Hello, everyone. My name is Yao Wenbin from Xidian University. My topic is learning-based roadside unit placement for C-V2X with uncertain traffic density and task demand. There are 4 parts in my presentation: scenario, challenges, method, and prospect. The C-V2X network architecture is shown here. We consider the roadside unit placement problem within one cell, and it consists of 3 entities: remote server via base station, MEC, roadside unit, and vehicle. In this architecture, vehicles can offload tasks either to the MEC servers via roadside unit or to the remote server via base station. Now, we have the system model. Our objective is to minimize total task offloading delay. Then there are 2 major concerns within this optimization problem: one where to place the roadside unit, and 2 for vehicles, which device to offload the task. Consequently, the problem is a joint problem to optimize the above 2 sub-problems. Besides, we consider the scenario as a grid road rather than a single road like our expressway scenarios. The second part is the challenge in this problem. Firstly, we introduce the mass model briefly. The model aims to determine the roadside unit's placement and offloading decision of vehicles to minimize task offloading. The objective function depends on decision variables position of roadside unit placement, offloading decision of vehicles, and 2 stochastic variables, task demand T and traffic density F. In order to evaluate the task offloading delay assigned with task demand T and traffic density F, we formulate the objective function as the expectation of the overall offloading delay via stochastic simulation. But the stochastic variables bring great difficulties in the deployment roadside units. So, we introduce roadside units placement in C-V2X network RPCN algorithm, a 2-step data-driven algorithm. The problem is decomposed into 2 subproblems: one the roadside unit position determination subproblem, and 2 the offloading scheme selection subproblem. The right part is the step 1 to solve the offloading scheme selection subproblem. The left part is the step 2 to solve the roadside unit position determination subproblem. The step 1 is stochastic simulation. The stochastic simulation is used to estimate the unknown characteristic quantity by sampling the uncertain task demand T and traffic density F for abundant times. Then we get these samples. For each sample, it's a certain problem. With deterministic TF and given roadside unit positions BD, the offloading scheme selection subproblem is formulated as a typical 0-1 integer linear program which can be. So, we can get the training samples for MLP. The step 2 is PSO particle swarm optimization with trained MLP. PSO is a meta-heuristic algorithm utilized to explore the optimal solution of positions of roadside units. The fitness of each particle is estimated by the trained MLP. The baseline algorithm determines roadside unit positions to balance the trade-off between efficiency of delay reduction and vehicle coverage based on traffic demand under a certain traffic density and task demands. In the left figure, we show the placement of row-side units of RPCN and baseline when row-side unit number is 4. In right figure, we show the overall task offloading delay by summing up tasks of all vehicles with different number of row-side units. Our algorithm consumes less time than the baseline. In this figure, the variation of total task offloading delay and number of vehicles with time is shown. Our algorithm shows lower task offloading delay and better performance in all time. All in all, the algorithm is uncertain programming with high practicability. In light of uncertain factors of stochastic traffic density and vehicle tasks, the learning-based algorithm is proposed to determine the placement of roadside units. By taking samples from real traffic data, the proposed algorithm is an offline method to determine the optimum roadside unit placement with high practicability. Then, the simulation results show the effectiveness of the proposed algorithm. In our future work, we plan to formulate the problem in a more complex network architecture with more communication entities. Secondly, realistic routes may be irregularly shaped, so we plan to formulate the problem in more realistic city scenario. Thirdly, with the consideration of urban traffic development, deployment strategy should be deployed in several stages rather than in one stages. At last, we want to improve the efficiency of the algorithm. We focus on the relationship between MLP and PSO and aim to design an appropriate MLP with new hyperparameters. Thanks for your listening.